this is welcome everyone, and thank you for joining, and I'm looking forward to this one and doing more in the future. I just want to go over a couple of things first here before we get into the meat of Tech Talk. So my whole idea with this is to take a look at how technologies work and where technology should be used. And I'm trying not to be too vendor specific about things, but I want to be more general so that we can take and do comparisons and you know, just have a look at the way things work, as opposed to, you know, what the marketing blurbs are on a particular product, and you know, kind of go past that, kind of delve into the spec sheets and make sure that we see what the specs mean, that kind of thing. We want to help you with planning with best practices. Get my lips to work right. With best practices for deploying some of this broadband wireless, and of course, after you've got it up in the air, we want to make sure that you have the tools to be able to measure the performance properly and troubleshoot in case there is troubles. That's the whole idea with Tech Talk, is that we'll look at things from the principal's point of view and go from there. So I'm trying to target this at people that are new to broadband wireless, I think, with little formal training, or to people who need a refresher. I'm not going to delve into university engineering level theory. I'm going to boil it down so that we get down to the things that we need. Maybe you got questions that you need answered that you've been wondering about for some time. Well, make a suggestion and go ahead and ask me the question, and perhaps I'll have a session that's specifically on that topic. And you know, hopefully, if you have a problem, give you a gentle push, and on we go. So who am I? Just for those of you who don't know who I am, this is I've been 40 years in the telecom industry in one form or another, almost all wireless. 20 years, the last 20 years in broadband wireless specifically. I've been a field technician. I've been a certified tower technician. Been an application engineer for a very long time, and been a system engineer now for I don't know, a dozen years or something like that. So got lots of experience, lots of time behind the wheel of my trucks in the past, and hope to impart that knowledge to you. And so just want you to relax and enjoy, participate as you want in the Zoom session here. There is a way to lift up your hand and to ask a question in the chat window, which I don't have open right at the very moment, but Nicole does. And so if there is a question, then we'll be happy to field it and go from there. So a little bit of info, my contact info, my email, dclelland@mbsiwave.com, and you can take and send me an email anytime. You can also get me anytime at marketing@mbsiwave.com and at support@mbsiwave.com. All right. Whoops. There we go. All right. So today, what I want to talk about is near and dear to my heart. One of the questions that I get asked very often is, you know, how far does this go? That's the basic question, is how far does it go? And the other questions might be around capacity, could be around what's non-line of sight, and questions like that. And it all boils down to the link budget. So I want to talk about in this little session the very basics of what the link budget is and what information that you can glean out of the link budget. So essentially, What we have in a broadband wireless system is we have data coming into an access point of some sort. The access point converts that Ethernet data into something that can be transmitted over the air, goes to an antenna, gets radiated out and propagated over a particular area. There's a receiver somewhere out there that picks up that signal and converts it back into the same Ethernet data, hopefully, that was brought into the access point in the first place. We're going to talk about the uplink and the downlink link budget calculations and what they mean, so let's take a look first at what the RF channel actually is. Very simplified, but essentially we have some device that modulates the as the data comes in. If we're going from left to right here on our drawing, we have a modulator. The modulator takes data from the Ethernet port in our broadband wireless case. It could be a serial port. It could be a microphone. It could be all kind of things. It comes in, turns it into some data form that can be transmitted over the air. Then we have the transmitter itself, the up converter, and we amplify it. So it comes out at some number of watts of power, perhaps, or at least some milliwatts of power, and goes to the antenna. The antenna then broadcasts or radiates the energy over whatever area the coverage is designed for. And then somewhere out there, there's a CPE device or a subscriber module of some sort that is going to receive that and take the signal, convert it down into something that can be demodulated, and then handed back out to the Ethernet port again, and the data be received. Then exactly the opposite happens in the other direction when we're going from the CPE device through up to the transmitter. It's exactly this process, just turned around, that's all. So we modulate, we up convert, we transmit, we receive, we down convert, and then we demodulate. So essentially, when we have a broadband wireless device, it is called a transceiver. So there's a transmitter and there is a receiver in the access point. There is a transmitter and receiver in the subscriber module. Very basic. Here's the basic modules of this process. Little more detail. So we have a network device that we're connected to, typically Ethernet, and so this device sends the frame to the Ethernet port of the radio. The Ethernet port then takes and stores it, clocks it out to a modulator in a way that the modulator can handle, and transmitter up converts it and amplifies it and sends it out to the antenna to be broadcast. This process, no matter what the device is essentially the same. There might be other steps in the way, but nonetheless, it's essentially this process for every time data is transmitted. The antenna, the purpose of the antenna is to take the energy that comes in an electrical form and transform it into an electromagnetic energy, so that we can then take and radiate this energy out. This energy then is useful to us because we can take and send it someplace and receive it. We're going to talk about how the transmit receive relationship is. That's one of the main points of a link budget. Many types of antennas, right? We have antennas that are designed to broadcast over a sector. They can be wide, up to 120 degrees of beam width. They can be narrow down to just a few degrees of beam width, depending on what the application is. I show here a typical cell tower with a number of sector antennas on the cell tower. We also have a parabolic antenna that has a very narrow beam width. And then we have a typical antenna that would be used at a subscriber's location that may have a 15 or 20 degree beam width, something like that. That is just just different types that are typically used in broadband wireless. Of course, there are other types of antennas, but we in the 1 to 10 gig range, these are the antennas that we typically use. I could have put a horn on there as well. That's an antenna that's becoming more and more popular because of its really good transmission characteristics, but nevertheless. All right, so let's start to get into some of the pieces that we need to know here as we are exploring how we get signal from one place to another. So the first characteristic or first principle that I want to look at here is thermal noise. Now, thermal noise is caused by electrons that continuously move, of course, and they bump into each other. They're excited by basically two factors: the temperature that they are at, and the bandwidth that they are vibrating or getting excited in, the bandwidth of the RF channel in our case here. There is a formula for thermal noise calculation. Quite simply, it's Boltzmann's constant times the temperature in degrees Kelvin times the bandwidth of our RF channel in hertz. So we can figure out what the power of the noise level is. On the right-hand side of this drawing, I kind of simplified it a little bit here. So thermal noise, as far as we're concerned now, is always a function of the channel width that our receiver is receiving. So what I've done here is I've taken and built a table here that has some different bandwidths on it, and what the power level in dBm of a typical noise floor is at that particular bandwidth. So for 15 kilohertz, I've got that in here because that's an LTE resource block, or an LTE OFDM channel, I should say. The 180 kilohertz is the bandwidth of a LTE resource block. 1 megahertz, 5 megahertz, typical broadband stuff, maybe 900 megahertz or other higher frequency equipment. We typically use 10 megahertz or 20 or even higher for broadband wireless equipment. So 20 megahertz channel has a noise floor of minus 101 dBm. So that's regardless of where it is or anything else, as long as the temperature is at 15 degrees Celsius or 273 degrees Kelvin, then we have this noise that's generated. This noise, it limits how sensitive our receiver can possibly be at any particular frequencies determined by the bandwidth of the channel. Now, every time that we do something with a signal, we take and we amplify it, we mix it with another frequency, we filter it, we modulate it or we demodulate it, whatever the case happens to be. Always the signal to noise ratio of the signal at the beginning of our process is always a little bit lower at the end of our electronic process, whatever that process happens to be. So if in the case of this particular process that I've got here, I've got a transmit chain and the data starts off at 50 dB above the noise. So my signal level, my desired signal is 50 dB above the noise. At the output of this, my signal will be 45 dB above the noise. Now, if there's an amplifier in there, that signal level is going to be much higher, but guess what? The noise gets amplified the same as the signal. So if I came in here at 1 milliwatt and came out of this process at 10 watts, for example, and at the input of my process, the thermal noise that's being generated by my electronics is 50 dB below that signal. It's going to be 45 dB below that signal on the way out. So I am generating noise every time I process that signal. Very important in link budget, because every time that we receive a signal, we add to the noise by some number. Typical noise figure, it's called, is around between 5 and 7 dB for most broadband wireless equipment. System on chip can be a little bit higher than say a DSP or an ASIC, but nevertheless, the noise figure, generally speaking, for our broadband equipment that we're used to dealing with is around 5 dB. This all come together in a minute here. All right, so here's a typical receive chain. We have a couple of things that we need to do in the receive chain. Like in the transmit chain, we took data that is at the Ethernet voltage level, and we converted it. We modulated and we amplified it to the point where it got to the antenna at some number of watts. So we take a voltage, we convert it into power, and we transmit that power. In the receiver, we do exactly the opposite. We take power from the air that's being received by our antenna, and we increase the level of it so that we can demodulate it. The demodulator then converts that energy back into a form of data that we can clock out to our Ethernet interface. In our case, we form it into Ethernet frames, and we hand it off to the device that's connected to the receiver, be it a switch, a router, a computer, whatever it happens to be. So keep this. This needs to be kept in mind, is that the receive process and the transmit process are not that much different from each other than the fact that one is amplifying to power and the other is taking power and turning it back into a signal that we can use in our network devices. Receiver sensitivity, want to talk about that. So we already know that the noise figure and the thermal noise level is the minimum signal level that we can receive and be able to do something with that signal. However, we need to be able to pass some sort of data, be it voice, be it whatever it happens to be in the case of analog radio. But in our world, in data radio, we want to pass a particular data rate of some sort. Now, we need to have the signal above the noise floor by some number, by some level, in order to take and receive that quantity of data. For example, in a particular channel, if our signal level was at the noise floor, at whatever the noise floor level is for that particular bandwidth, we would have a 0 signal to noise ratio. In other words, our signal is the same level as our noise. And at that rate, we probably would barely be able to decode just a few bits per second. We would have trouble with that. So as we increase the signal level, as we increase the signal above the noise, we then can take and pass more and more data. So when we are designing a telecom network, we want to take and have a minimum amount of data that we're going to pass from one device to another. So let's say in our case, we're talking about an internet provider service, and we want to pass 20 megabits as a minimum service level. Well, it's going to take a certain amount of signal above that noise to be able to pass that 20 megabits. We need to know what that is, but that's essentially the definition of the receive sensitivity. This sounds simple, and it sounds really. I want to say that it sounds really basic, but it's important in our application of a link budget. We need to know that we don't have an unlimited sensitivity at our radio. We have to have a floor that we're going to maintain as our minimum level of connectivity, and so we do that. That's called receive sensitivity. All right, now we can't. Today, data rates are all way too fast to actually turn a transmitter on and off digitally and send the data from one place to another. Those days kind of ended with Morse code. And so even in Morse code days, people could actually operate a Morse key faster than what sometimes the channel that they were sending the information down could go. So what we do is we take and we modulate a carrier. We take and transmit a carrier. We adjust characteristics of the carrier. So we change the amplitude, we change the phase, we change the frequency. We do many different things to it. Typically, though, these days that we're doing what's called quadrature amplitude modulation. And so what this means is that we have a number of different states. For example, QPSK or 4-QAM has 4 different states that the carrier can be in. And then our receiver needs to be able to decode these 4 different states. It needs to be able to see what the 4 different states are, or 16, or 64, or 256, whatever the case happens to be. And we have in point-to-points where we have a very tight beam width on our channel, we can actually take and go up to very high levels of quadrature amplitude modulation. The one thing that you need to remember about all this, and I got some tables in here that and in the worksheet that we're about to that we're going to look at, has some minimum signal to noise ratio requirements to be able to decode that particular level. Now, sometime I'll do another session like this on modulation itself and what that actually means. But for the case of link budget here, we just need to know that the higher the level of modulation that we want to decode, the more signal above the noise that we need to be able to do that. So most manufacturers now in their data sheets will specify at a particular channel bandwidth, they'll specify a modulation and a data rate that applies to that particular modulation, and they will tell you what signal to noise ratio that you need for that particular data rate. So in our case here, I used a 450i spec sheet here. I took a little piece of it, and we can see that we have QPSK, 16 QAM, 64, and 256 QAM, and we need 10 dB as a minimum of our signal above our noise to be able to decode that QPSK signal. Then we, as we go up in modulation states, in modulation complexity, then we need more signal to noise ratio to be able to decode it. So 16 QAM, 17 dBi, or 17 dB, I should say. 64 QAM, we need 24 dB. 256 QAM, we need 32 dB. This is universal across all broadband devices, is that there's going to be, if they're capable of supporting multiple modulation rates, there will be a signal to noise ratio minimum that you need to be able to decode that particular modulation level. So the main calculation that we're going to talk about today is going to be system gain. We're going to relate system gain to range ultimately here before we get finished this our little treatise here. So in our system gain calculation, we take the characteristics of the transmitter, the transmit chain, I call it here, and we add to that the processing power of the receive chain to come up with the system gain. So there's a couple of different ways to express the formula. So let's look at the first one here. System gain, which is always expressed in dB, is the transmit power out minus the antenna cable loss to connect the antenna to the transmitter, plus the transmitter the transmit antenna gain, plus the receive antenna gain at the other end, minus the receive sensitivity that we need. Or we can express it as break it down a little bit more. Take that receive sensitivity and break it down into its components. So we have transmit power out minus the antenna cable loss, plus the transmit antenna gain, plus the receive antenna gain, minus any receive antenna cable loss that there is in case our receiver has some significant amount of cable between the antenna and the receiver, minus the noise floor at the particular channel bandwidth, minus the signal to noise ratio, the minimum signal to noise ratio required to pass our data, minus the noise figure. This is the system gain calculation. So when we add and subtract these components up, we come up with a particular level. Now, I have let me take and open up one more thing here that I was ready for, but of course now that I had to restart my computer, I'm not. Let me just drag this over here for a second, and let's go here. And oops, there we are. Okay, let me drag this up here. Let me make this full screen. All right, so I want to take and let's view a little bit bigger. Let me zoom a bit. Probably not that much. Let's go back to 100%. All right. So here I've created a worksheet that I have the parameters here in blue that I want to take and use as my my parameters for the system gain calculation itself. So you see I have base station transmit power, I have antenna cable loss, I have antenna gain, I have receive sensitivity number here of 8 dB for the typical the data rate that I've picked. I have two-stream diversity in this case. I haven't talked about that yet, but I will talk about that in a bit. And then, of course, in the uplink, I have exactly the opposite. I have the CPE transmit power and the same characteristics, and the base station sensitivity over here. So we have the specifications, and this is directly from. We can take this directly from the spec sheet. So then I have some more frequency, or some system parameters, I should say. I have the frequency, which I've selected here as 3650. I've got a particular bandwidth. I've added a spectral efficiency that may or may not be in the specification sheet. And I have chosen a couple of other parameters here that we'll talk about in a bit here. I've got a minimum installation SNR, and I've got a downlink, uplink percentage that I've included in this, and I've included my noise figure, of course, which could be up here in the blue in the system parameters. Now, if I calculate my downlink system gain, I've taken everything that we showed right in the slide and added up here. And in this particular case, with a 1 watt transmitter and a 17 dBi antenna, and a 15 dB or 19 dB gain antenna on the CPE, well, we come up with a downlink system gain of 158 dB. It's real typical that we see numbers in the 140s and the 150s, sometimes as high as 160, depending on the equipment, but 150s are real typical. The other thing that you notice here in this is that my downlink system gain and my uplink system gain are two different values. Why is that? That's because I have more power in the base station in the downlink than I have in the CPE transmitting in the uplink in this particular case. If I took and made these the same, then you'd see that I would have 158 in both directions. So, but if my CPE transmit power is only 23, then we see we have some difference in our system gain. I'll talk about what this means in a minute here. All right. Now, I want to make another definition here that we go. So the next definition that I want to take and introduce to us is a term called MAPLE, or maximum allowable path loss. Now, when we take and calculate our system gain, there's a few parameters in here that are missing. So one of them here is that we don't have any of the transmission impairments that we might normally see in the world. The most significant one, of course, is free space loss. That's we have to calculate that. Maybe we've got fading. Maybe we've got some non-line of sight. We'll talk about all of these as we're going along here. But the goal of calculating a link budget is to know what range a subscriber unit can be installed in and give a reasonable expectation that the link will work, or master and slave, or whatever it is you want to call it. But that's the goal here, is to provide a reasonable expectation that the link will work. Now, there's always anomalies that we can't calculate in here, like interference, for example. We can account for it if we know it's there, but maybe in the beginning we don't know it's there, or maybe it wasn't there, and so we have some data problem, some throughput issue or something, and we want to take and make sure that our link, that the equipment is still performing at the rate that we installed it at in the beginning. So we need to calculate the link budget. Now, let me talk about propagation here for a bit. So that part in between the two antennas, between the transmitting and the receiving antenna, is reciprocal in both directions. I want to talk about a few of the characteristics of the RF channel. So the RF channel has a particular width. That's the amount of bandwidth that we transmit, the amount of bandwidth that we receive in the receiver. So we know that. We know it's got some bandwidth. Propagation through the air or through free space between my antennas is reciprocal. If I have so many dB of loss between the tower and the CPE, I always have the same amount of loss between the CPE and the tower. So both directions, exactly the same. Propagation characteristics change with the frequency. So in our case, as we go up in frequency, our propagation loss gets higher for the same distance. As we get higher in frequency, maybe moisture in the air begins to make a difference. As we approach 30, 40, 50 gig, 60 gig, oxygen in the air can make a difference in the propagation characteristics. There's many things that can happen here. I don't want to talk about that too terribly much now. That's a topic of maybe of another tech talk here, but nevertheless, it is different as we change frequency. As we go lower in frequency, the propagation loss reduces. That's one of the reasons why some operators use 900 megahertz in some areas, is because you can still pass a broadband signal over 900 megahertz and deliver 10, 15, 20 megabits of performance perhaps down at 900 megabits or 900 megahertz, I should say, and we have more energy that we're able to take and deliver to our CPE devices. But let me step back a bit. The transmitting antenna radiates power in every direction, no matter if it's designed to go over a 60-degree horizontal beam width sector. There is energy that is going in every direction. It's just more energy in the direction that it's designed to go. Radiating elements of this antenna have a particular size. They have length, they have width, they have height. The receiving antenna has the same characteristics of some sort. It might be different, of course, but they have length and width and height also. So free space loss, its definition is the ratio of the radiating elements, the receiving elements, and the area of the RF energy's wave has expanded over in the distance between the two antennas. So I got, oops, let me go back here. I have a simple little graphic here. In this graphic, we have an antenna that's transmitting in the center of this. We have our energy radiating out in every direction from this antenna. Then at some point in time out in space here, we have our receive antenna. It's in this case, let's say it's at the end of this, at this arrow. So what is free space loss? So free space, the energy that the receive antenna can capture is related to this energy that the transmitting antenna has sent out. But you can see here that we're sending energy in every direction, but our receive antenna is only intercepting a very small portion of that wave that was radiated. So the difference between the power transmitted here and the energy that we can intercept right at the receive antenna because of its size is free space loss. The bigger the receive antenna, the lower the loss. The farther that we have the transmitter apart from the receiver, the bigger the area of the wave is, and so the lower the energy is that's intercepted by the receive antenna. There probably are 20 different ways to express this mathematically, and different engineers will have different favorites. My favorite is the simplest. Free space loss in decibels is this 32.5 factor plus 20 times the log of the frequency in megahertz plus 20 times the log of the distance in kilometers. If I want to do this in miles, 36.2 plus 20 log of the frequency in megahertz plus 20 log of the distance in miles is the formula. But since we in the scientific world are metric, we're going to stay metric. So we're going to stay in kilometers, megahertz in kilometers. So this is the formula. 32.5 times 20 log of the frequency plus 20 log of the frequency plus 20 log of the distance. That is the loss that we would expect to see in a signal transmitted from one point and received at another point some distance away. So we can see here a couple things. The higher we go in frequency, the bigger this factor, bigger the 20 times the log of the frequency factor is. So the loss is lower if this were 900 megahertz as it would be compared to 5,500 megahertz, for example, or 5,800 megahertz, much different. Turns out that every time you double the frequency, you increase the loss by 6 dB. And every time you half the frequency, you reduce the loss by 6 dB. Now the same thing goes with the distance. So oftentimes we can't change the frequency. We're given the frequency to transmit in, and that's what the equipment does. But we have this distance parameter here as well, and it is also a square of the distance. It's related to a square of the distance, 20 times the log of the distance in kilometers. So the farther we go, the more loss there is. The shorter we go, the less loss there is. And so this too, every time that we double the distance, we increase the free space loss by 6 dB. Every time we half the distance, we decrease the loss by 6 dB. So for example, if at 3650 at 3 gig, at 1 kilometer, I had 104 dB of path loss. At 2 kilometers, I will have 110 dB of path loss. At 4 kilometers, I will have 116 dB of path loss. So, and if we change the frequency, then we're going to either increase or decrease by that amount as well. So this is pretty easy to figure out. And in my little worksheet, if I go back to how do I get there? I don't want to take this out, just not just yet, but I'll go back to the worksheet and I'll show you in a second here. This real important to be able to calculate this. So once we get to know the distance that we want to go, or in this maple formula, now we can take and determine what the maximum number here is that we can go. So when we, let me go back up to Maple here. So when we're calculating our maximum allowable path loss, our system gain minus our transmission impairments that we have that we know about equals the maximum distance that we can go. So if we have a system gain of, let's say, 140 dB, and we need 20 dB for the signal level that we want to be able to pass, then that means that our maximum allowable path loss is 120 dB. So then we can work this backwards into this formula, which I'll do in the worksheet. I'll show you how to do that. And we can come up with a range, a maximum range that we can deploy CPE in to meet those characteristics. Now, this is free space loss. It doesn't take terrain into account. It doesn't take trees and clutter or anything else into account. And we'll talk about that in a minute. But this is the farthest that you can go when you have line of sight between your two antennas. I want to talk about another parameter that we need to look at here, and that is fade margin. So this is a plot from a spectrum analyzer. As we take and we measure RF that comes out of a receiver, this is the kind of pattern that we see. We see at different moments in time or different moments in frequency over a broadband signal, we see some signal levels high, some signal levels lower, and everything in between, more or less. Now, if I were to take and calculate my free space loss here, the top of this is going to be, or this 0 dB line here in my signal input, is actually my free space loss calculation. So you can see that I have very little of the time. I have signals that mix with each other and boost their amplitude. We can ignore those. That's kind of irrelevant here in our calculation because of the fact that it doesn't happen often enough. More often than that, we have signal levels that are lower than our free space loss by some amount. So in this particular case, I don't want to get into the math to calculate availability, but we have a case where this blue line on this particular signal represents the spot where if our signal level is above that, we about 70% of the time we are above that level. That would mean 30% of the time that we're below that level. The red line here means that 25% of the time we're below that line, and 75% of the time we're above that line. So at some point we have to take and decide that we want to increase our signal by in order to get the availability that we want. This is called fade margin. And so in this particular case, if I were to measure this and decide that this is what my signal level looks like, it looks like to me that I need about 6 dB of fade margin. I need my signal level to be 6 dB above the level of free space loss here in order to take and have more than 70% availability. This number is real important for data rate and for customer satisfaction. If I were to deploy the network designed around this red line, if I were to just use free space loss, I could expect that in many locations I would be available at that particular data rate less than 25% of the time. So that would mean that if I'm selling say a 25 megabit service, this customer might actually be able to achieve 5 megabits or less most of the time. So that would be quite detrimental. I could do another hour lesson just on this availability to be able to describe how you calculate this and what you do with it. But it's from the point of link budget, it's not that important. The important thing is that we have to take this into account when we're doing our link budget. So I don't want this to be the edge of my coverage. I will actually want 6 dB more signal. So I really want to move this up. At this point, I don't want to install CPE just at that range. I want to install it shorter than that, so my signal quality is this much better. This makes sense? Here's another way to look at it. What we've done in this case is we've taken and we've measured all of the CPE locations that we plan to install on a particular sector, and I plotted them on a graph. So in this particular case, I've got CPE locations that are between 100 meters and 10 kilometers in this graph. As you see, as we get farther and farther out, and this is all line of sight still, as we get farther out, my signal becomes more variable all the time. The range at a particular distance, so let's say at 2 kilometers, the range, the minimum range to the maximum signal level at that 2-ish kilometer range is actually quite large. And so I need to be able to compensate for that. This is another expression of fade margin. This is another way to look at it. So in this particular case, I need to then not assume that my red line here is going to be my minimum level, because I need to add some signal level to this in order to take and maintain the performance that I want at that particular distance. So these are all planning. These are planning calculations that I make in order to determine what I need to do. So I add fade margin. I have some recommendations as to the amount of fade margin that I should add. So typically speaking, in our broadband networks that we deploy now, if I had no diversity, in other words, if I had a single data stream, I should add about 12 to 20 dB of level, or reduce the range by 12 to 20 dB in order to increase my minimum signal level for the data that I want to supply. As we do diversity now, so we have 2x2 diversity, it's a single data stream repeated twice. I should be in the 4 to 6 dB range as my planned diversity. If I have 2x2 diversity, but I'm in MIMO B now, I have a dual data stream, I have to increase that a little bit. So I recommend in the 6 to 10 dB range. 6 dB here is kind of the common number that we should consider for a high quality service. If I'm using 4 stream or higher diversity, then I'm in this 3 to 6 dB range. So, you know, massive MIMO arrays such as the 450M and some 5G LTE configurations, I recommend that as we plan for it, that we use dual diversity, dual data stream values here as the minimum fade margin. So 6 dB here seems to be a common factor. If we go less than 6 dB, then as long as the range is real short, we're okay, because as we showed already, the farther we go, the wider this gap, this range, this fade margin needs to be in order to support it. So, got some other propagation factors here that I want to talk about. So, at frequencies above 1 gig, terrain will block all the signal. So, there's a hill in the way, very little usable signal will get over the hill. The calculating the range is kind of out of the scope of this discussion, because I don't want to get into terrain and its contribution. That becomes like we're building a planning tool then at that point, a heat map tool at that point, and that's not really the point here. The point here is to know how far that we can go, and then lay that circle, if you like, on a map onto say Google Earth or something like that as a rudimentary planning tool, and where the terrain allows us signal to our transmitting location, we can take and cover it there. But that's the the principle here is that terrain blocks the signal. Trees and vegetation, the effects related to frequency and diversity, and but generally speaking, trees in our northern hemisphere are about 150 dB per kilometer of loss. So really difficult to non-line of sight, penetrating lots of trees, we end up with no signal at the end of it. Nevertheless, the effect, the point here is that the effect is related to the frequency. The higher the frequency, the more attenuation the trees and the vegetation cause. Last but not least is multipath here. I want to take and talk for a minute about what multipath is. Essentially, in multipath, just as the name describes, we have multiple modes or multiple RF paths between the antennas. As we take and increase the number of modes or paths that we have in between the antennas, our attenuation increases. And so I've got a way to look at it here that's a little bit different. Most of the time when you see somebody talking about multipath, they talk about reflections off objects. And so they to demonstrate it, they draw it as reflections off the object. But when you have a tree or a group of trees or grove of trees and you're going through the trees, there's not much reflecting off of there. The trees are doing something else to the signal. So in my mind, we can view the electromagnetic spectrum similar to water flowing in a lake or smoothly on a river. If we consider our transmitter to be injecting dye into the water at a particular spot, the dye will take and flow downstream and disperse slightly as we're going along. Now, when in the RF world, when we hit a grove of trees, it's like rapids. It's like we hit a rapid. And so you can imagine what would happen to that dye as it flows smoothly down the river and then hits this waterfall. The dye gets dispersed, the water is churned up, and if we had an antenna that was in the middle of all of that chaos that's over the waterfall, much less of the water would actually hit the antenna, or much less of the dye would actually be intercepted by the antenna than it would be if we were in this clear flowing water in our lake or a river. So if we look at multipath that way, there's some characteristics of it that are obvious. The closer that our receiving antenna is to the obstacle that's causing the multipath, the more attenuation that we have. As we take and move farther away from that obstacle, the flow will smooth and we will be able to actually recover more of the signal as we drift away from that obstacle. So it's important to know this characteristic, that when we have a CPE that's located, let's say, right in the middle of a forest, our attenuation from that forest is going to be much more than if we have the CPE installed at the very same height, maybe even, once we get past the trees. So if we're, say, a kilometer past the trees, our signal level might actually be higher than it would be in the trees themselves. Line of sight we can consider to be essentially the lake itself. No rapids encountered. Non-line of sight, we encounter rapids or other obstacles in the water. That's a great way to look at this. So now let's take what we've learned here and let's apply it to our information that we know. So let me get out of this just for a second and go back to where's my spreadsheet? It's got to be right here. There we go. Okay. Okay. So now we've got some parameters here that we talk about. So I've decided here that in order to pass the data rate that I want to with this particular system, I need to have 22 dB of SNR. And if I scroll over here a little bit, I've got some basic levels of typical modulations and the SNR required to decode those modulations. So I've picked 64 dB or 64 QAM at 22 dB, and I've used that in my formula here. So knowing that when I calculate my system gain, my system gain has got a receive sensitivity of 8 dB, but I've taken and I want 22. So I want more than that. So my downlink maple is actually 20 dB less than what my system gain is. So my downlink maximum allowable path loss is 138 dB. That's the most that I can lose and still pass this this signal at my 22 dB SNR. So what does that mean? That means that with this maple, that means my downlink maximum range is, in this case, is 52 kilometers at this 3650. My uplink maximum range, using the parameters of the that I've used here in the equipment specification, is 23 kilometers. So what that means here then is that in order to pass the uplink data that I want here, even though I can go 52 kilometers in the downlink, this 23 kilometers is the maximum that I can install this CPE at line of sight. That's the way that once I understand what my maple is, then I come up with these values here, and we can take and know then that my range for sure is going to be less than that. Now, if I have interference or have other anomalies, let's say that I want to take into account 20 dB of obstacles. So let me just plus obstacles. So at 5 dB, that means I've only taken noise figure into account, not obstacles. But if I want, say, 20 dB of obstacles, I can make this 25 dB, and then when I work this into my calculation, now, why didn't my sheet work? Okay. So in this particular context here, at a CPE that's at 3.5 kilometers away, I think if I change this, that probably changes that number. I would expect to see a neg 75. I would expect to see a neg 49 dBs signal RSSI at that point, and my expected SNR at that point would be 47. But if I actually put a CPE out there and I see that it's actually at neg 75, then I know that I've got 16 or so dB of non-line of sight and extra noise contribution. I don't know what it is at this point, but I know that my numbers of what I'm really seeing are less than what I would expect to see at that particular point. And so this is the way that I can determine, from a mathematical standpoint anyways, very simply, what my transmission impairments are for that particular 3.5 kilometer link in this particular network. Let me go over here. Let me, all right, I put some converters here on this particular sheet. So if taking the free space loss formula into account here, let's look at just a few of these here. If I have 20 kilometers of link distance, my contribution to my free space loss is 26 dB. If I make this 10 kilometers, Look, it's 20 dB. So it changed by 6 dB. So 6 dB less, or half the distance, 6 dB less loss. If I go to 40 kilometers, then I'm going to be at 32, which is 6 dB more than what I was at 30, or at 20, I should say. And so there's my 6 dB relationship there. If I changed my frequency from 3650 to 5500, let's say, then I'm going up by 4 dB. It's not quite doubling the frequency, but I've gone up by 4 dB for the contribution of the frequency factor to my free space loss. And of course, if I change my channel bandwidth, then my noise floor changes accordingly. And so you have work that into the maximum allowable path loss calculation, and we have a bit of a system. Then at that point, we can take and understand a little bit better what we would expect at a particular range, at a particular system parameters as to what we would expect out there. And I want to take on some of the next ones here, I'm going to take and dig into this a little bit deeper. I think that as I was going over this, I thought this was a good introduction, but I want to take in some of the next tech talks as we go along here, I want to take and get a little bit more detail into some of these parameters and these principles, and relate them back to specific equipment, so that we can talk about what a particular system, whether it be LTE or OFDM or whatever it happens to be, the characteristics of it are at these particular frequencies and the bands that we're able to use. So with that, let me go back to. All right. All right, so to finish this up here, practical uses for an accurate link budget. So pre-deployment, of course, range planning, and to a certain extent, the capacity estimation and dimensioning. We know if we pick a particular service level that we want to supply to our subscribers, we know what the minimum signal to noise ratio would be, or the signal strength would be that we need to be within in order to take and provide that information. And so we can use that for our pre-deployment planning. Post-deployment, the biggest use of the link budget is for RF troubleshooting. If I have an antenna and I suspect that it's had some water in the antenna cable or something like that, my signal levels have dropped off, maybe my throughput has come down, I can take and rerun my link budget for that specific CPE or that specific situation, and know that if I meet my link budget, then I know my RF is okay. I'm gonna look for something else. If it's not, if I don't have the signal strength that I used to have, then I can take and break my network down and decide whether it's my antenna cables at my access point, or maybe I have a bad CPE antenna, or maybe it's just blown off azimuth or something like that. Who knows? But anyway, but the link budget will tell you right off the bat whether this particular link is working the way that it's supposed to. If I'm receiving interference, sometimes I don't know that I'm receiving interference, but the performance of the equipment behaves as though it's interference. So rather than jumping up right away and changing frequency and seeing what happens, I can run my link budget, and I can know what the difference between the performance I'm getting and the performance that I expect is, and then from that number, I can tell if it's interference or not. So for example, if I was having a problem on a particular customer site, and I run my link budget, and I find out that there are only a couple of dB difference in SNR and RSSI that I would expect from my link budget, then I'm pretty sure that's not interference. I need to go looking for something else. So maybe I've got a bad Cat5 cable, or maybe I've got something else that's the matter, a switch or router or something like that. Who knows, right? If I'm going to take and deploy, let's suppose I plan a network and I know that I can go 12 kilometers with this network. And so I get out to installer goes out to install a CPE at say 6 kilometers or something like that, or 4 kilometers. And I'm getting, 6 or 8 or 10 or 20 dB less than what I would expect from the link budget. The link budget tells me what I should get there. And then if he's surrounded by trees, or I know it's non-line of sight, I can estimate the effect of the trees, and then I can determine what I want to do next. Do I want to raise the CPE? Is it okay the way that it is? Or whatever the case happens to be. But at least I have a baseline to be able to troubleshoot from. Same with capacity verification. And the number one thing is get the magic out of it and eliminate RF issues when troubleshooting network issues. Quite a number of times I've taken and been involved in troubleshooting networks, and simple link budget calculation, made the spreadsheet up just right on the spot, and calculated link budget, and it turns out that RF is okay. I got a problem somewhere else. Maybe I got a problem with QoS, or I got something else. But it eliminates the RF issue right away when I meet my link budget. So, want to thank you for joining me for this this little presentation. I hope it was enjoyable. I tried to speed along as much as we could with the late start. I apologize for that. And if you've got any feedback, comments, new topic suggestions, please send them to marketing@mbsiwave.com, and we'll be happy to look at them and spin up a presentation and talk about this. If you have the question, chances are pretty good that somebody else does too. So I want to thank you, and I really enjoyed our hour together.
Thank you so much, Dave. I just want to give everyone one last moment. If there's any questions or anything that someone wants to throw into the chat window, please speak now or forever hold your peace. If not, we will talk again in 3 weeks for the next Tech Talk. All right, Dave, that looks like it. Thank you, sir, and looking forward to the next session.
You bet. Take it easy, and we'll talk to everybody soon. Have a great day.
Bye, everybody.